Right now, every object in the outer solar system is being slowly herded. Something enormous is directing traffic in the darkness beyond Neptune, nudging icy bodies into synchronized orbits with a precision that 8 planets simply cannot produce. We cannot see it. We have never photographed it. But the gravitational fingerprints it leaves behind are so precise, so mathematically consistent, that the probability of them arising by chance is estimated at less than 1 in 1,000. That number is not a guess. It comes from careful statistical analysis of some of the most distant objects ever catalogued in our solar system. These objects, known as sednoids and extreme trans-Neptunian objects, are clustered in physical space in a way that contradicts everything we understand about how solar systems evolve over billions of years. In a stable 8-planet system, these distant bodies should be scattered at random angles across the sky. Instead, they are aligned, orbiting in a synchronized formation that points toward a single, unseen source of gravity. What scientists are dealing with here is not a subtle anomaly. It is a persistent, measurable, reproducible signal that has appeared in multiple independent datasets, across multiple surveys, analyzed by multiple research teams. And as of early 2026, the search for the object responsible has entered its most critical phase yet. Before we go further into the modern evidence, it is worth understanding why this kind of planetary prediction carries weight. The history of astronomy contains a remarkable precedent that changed how we approach unseen objects in space. In 1846, a French mathematician named Urbain Le Verrier was not looking at the sky. He was sitting at a desk, working through equations describing the orbital motion of Uranus. The problem he encountered was deceptively simple. Uranus was not where Newtonian physics predicted it should be. It was speeding up and slowing down in ways that could not be explained by the gravitational pull of the Sun and the other known planets. The deviations were small, but they were real, and they were reproducible. Le Verrier did not conclude that physics was broken. He concluded that there was another planet, one that no one had yet seen, exerting a gravitational influence on Uranus. He spent months working through the mathematics, calculating exactly where this hypothetical object must be, how massive it would need to be, and what path it would travel around the Sun. When he was finished, he sent his coordinates to astronomers in Berlin and told them precisely where to look. They found Neptune within 1 degree of his prediction. On the very first night they pointed their telescope at the location Le Verrier specified. They found a new world. This is not just a historical curiosity. It established one of the most important methodological principles in planetary science. Gravity is a tracer. When a known system behaves in unexpected ways, the most logical explanation is the presence of a hidden mass somewhere in the vicinity. You do not need to see the object to know it is there. You need only measure the gravitational distortions it leaves in the motions of other things. We are currently living through a second Le Verrier moment. The evidence is not visual, it is gravitational, and the case has been building for over a decade. The modern story begins in 2003 with the discovery of Sedna. Sedna is a small, reddish world with an orbit so elongated and so distant that it defies easy explanation. At its closest approach to the Sun, it comes no nearer than 76 astronomical units. 1 astronomical unit is the average distance between Earth and the Sun, roughly 150 million kilometers. At 76 astronomical units, Sedna is already nearly 3 times farther from the Sun than Neptune. At its most distant point, Sedna swings out to about 940 astronomical units from the Sun. What puzzled astronomers immediately was that Sedna's orbit should not exist in an 8-planet solar system. with no large object in the outer system to place it there, and no mechanism to explain how it arrived at such a distant, elongated orbit. Sedna was classified as a mystery rather than a solution. Its discoverer, astronomer Mike Brown at Caltech, knew that something unusual had shaped that orbit. At the time, he was not yet sure what. Over the following decade, more objects like Sedna were found. They were called sednoids, and they shared key orbital properties. Each of them had perihelia, meaning their closest approach to the Sun, well beyond the influence of Neptune. Each of them traveled on highly elongated paths, and critically, they were all oriented in strikingly similar directions in space. In 2012, and again in 2014, Scott Shepard and Chad Trujillo began to formally document this clustering. They noticed that a specific orbital parameter, the argument of perihelion, was not randomly distributed among the most distant trans-Neptunian objects. Instead, it was concentrated. The angles were bunched together in a way that could not easily be dismissed as coincidence. In 2016, this observation was turned into a formal hypothesis. Konstantin Bettigin and Mike Brown at Caltech published a detailed mathematical model showing that the clustering of these distant objects is not a statistical accident. Their simulations demonstrated that a ninth planet with a mass roughly 5 to 10 times that of Earth would naturally shepherd these smaller bodies into the specific synchronized orbits we observe. Under their model, this hypothetical planet sits on a highly elongated orbit of its own. At its closest point to the Sun, it approaches no nearer than approximately 200 astronomical units. At its most distant, it could be as far as 1,000 astronomical units away. Its orbital period, the time it takes to complete one full trip around the Sun, would be somewhere between 10,000 and 20,000 years. We are talking about a world so distant and so slow that ancient human civilizations were just beginning to develop writing the last time it was close enough to be in the same general region of the sky as where we are searching today. The Bettigin and Brown paper ignited a wave of follow-up research. Some groups tried to replicate the statistical analysis with larger datasets. Others probed the sensitivity of the model to changes in the planet's assumed mass or distance. Still others began designing observational campaigns to search the sky for the object directly. But not everyone was convinced. Critics pointed out a potential flaw. The known population of distant trans-Neptunian objects is small. At the time of the original paper, only around a dozen objects were used in the statistical analysis. A dozen objects is a thin foundation for a major claim. And more importantly, those objects were not discovered through a uniform, unbiased sky survey. They were found by telescopes that could only search limited portions of the sky. If astronomers were only searching in certain directions, the apparent clustering might simply reflect where the telescopes were pointing, not a real physical alignment. Bettigin and Brown took this criticism seriously. In their subsequent work, particularly in a comprehensive 2019 review and in the landmark 2024 analysis, they incorporated models of observational bias directly into their statistical framework. They did not ignore the possibility that the clustering could be an artifact of incomplete sky coverage. They built that possibility into their equations and then asked whether it could explain away the signal entirely. It could not. Even after accounting for the limitations of past surveys, even after removing the most questionable data points, even after adjusting the analysis for the specific regions of sky that past telescopes could and could not access, the requirement for a ninth planet remained. The gravitational signal was too strong, too persistent, and too consistent across too many independent objects to be explained as a telescope bias alone. The 2024 paper introduced a new and particularly compelling line of evidence. This time, Instead of focusing on the direction the objects were pointing, Batygin and Brown analyzed the survival of a specific population called Neptune-crossing trans-Neptunian objects. These are icy bodies whose orbits bring them periodically into the orbital zone of Neptune. That sounds relatively benign, but the physics are brutal. Neptune is a giant. When one of these small objects gets close enough, the gravitational influence of Neptune either pulls it inward toward the inner solar system or flings it outward into interstellar space. The encounters are powerful and frequent, enough that any object in a Neptune-crossing orbit should be cleared out within a few million years. A few million years is an incredibly short timescale in the context of the 4.5 billion year age of the solar system. If these objects have been in their current orbits since the early solar system, they should have been gone long ago. Yet they are still there. We see them. We have catalogued them. They are a real and persistent population. Batygin and Brown used unbody simulations to ask a very precise question. Can the 8 known planets account for the continued existence of these objects? The answer was no. Without an additional source of gravity, the simulations showed that Neptune crosses at the relevant distances and orbital configurations would have been ejected or destroyed in a tiny fraction of the age of the solar system. But when they added a 9th planet with the predicted mass and orbital parameters into the simulation, the picture changed dramatically. The distant world acts as what the paper calls an orbital shepherd. As the small objects drift too close to Neptune, the gravity of the 9th planet exerts a subtle but consistent counterpull. This pull, acting over millions of years, keeps the objects in a state of gravitational resonance that shields them from Neptune's disruptive influence. Planet 9, if it exists, is actively protecting a population of small bodies that should otherwise not exist. The statistical significance of this finding is worth emphasizing. The researchers calculated the strength of this evidence at the 5 sigma level. In the scientific community, 5 sigma is the gold standard threshold for declaring a definitive discovery. It means the probability of observing what we observe by pure chance alone is roughly 1 in 3.5 million. This is not a suggestion or a statistical curiosity. At 5 sigma, scientists in particle physics declare new particles discovered. At 5 sigma, signals are considered confirmed. The 5 sigma result does not prove that Planet 9 exists, but it means the null hypothesis, the idea that there is no Planet 9 and the observations arise purely by chance, has been statistically demolished. Something is out there maintaining the orbital architecture of the outer solar system. The most straightforward explanation remains a massive 9th planet dot. Now, knowing that something is out there is not the same as finding it. The challenge of actually detecting Planet 9 is one of the most technically demanding in the history of observational astronomy. The difficulty begins with a basic law of optics. Reflected light falls off with the inverse square of distance. This means that if you double the distance between a planet and the sun, the amount of sunlight hitting that planet drops to 1/4. If you triple the distance, it drops to 1/9. A planet at 500 astronomical units receives roughly 25,000 times less sunlight per unit of surface area than Earth does. That light then has to reflect off the planet and travel the same enormous distance back to our telescopes. The total drop in signal is staggering. A planet at that distance would be roughly 600 times fainter than Pluto, and Pluto is already famously difficult to detect. This is why Planet 9 has not been found by simply pointing a large telescope at the sky and looking. Standard optical cameras at normal exposure times cannot see it. The planet would be a faint smear of light, barely distinguishable from the statistical noise in the image detector. It would require exquisitely long exposure times and sophisticated image processing just to produce a marginal detection. But researchers have developed a set of strategies to work around these limitations, and they hinge on a property of physics that is harder to hide: heat. Even a cold, distant world like the one Bettigen and Brown predict would still have residual thermal energy from the process of its formation. Planets form through accretion, the gradual collision and merging of billions of smaller bodies over millions of years. This process releases enormous amounts of gravitational potential energy, which is converted into heat. A planet with 5 to 10 times the mass of Earth retains a meaningful fraction of that heat even after 4 billion years of slowly radiating it away into space. The heat that remains is radiated as infrared energy, specifically in the longer wavelength portions of the spectrum. While the planet is nearly invisible in the optical range of light, it should glow faintly but measurably in the infrared. The key is to look for a moving point of thermal emission against the static background of stars and galaxies. This insight shifted the focus of the search toward archival data from space-based infrared observatories. One study published in 2025, led by researcher Kevin Fang, took a creative approach to the problem by exploiting the time gap between two separate sky surveys. The first was the infrared astronomical satellite, known as IRAS, which conducted an all-sky infrared survey in 1983. The second was the Akari satellite mission, a Japanese space telescope that surveyed the sky in 2006. These two surveys are separated by 23 years. At the predicted distance for Planet 9, an object would move across the sky so slowly that it would appear essentially stationary on timescales of days or weeks. Over the course of a year, it would barely shift, but over 23 years, it would have moved enough to be detectable. If you know what you are looking for, the technique used is called shift and stack. By layering multiple images, taken at different times, and adjusting them to account for the predicted motion of a slowly moving object, researchers can mathematically amplify the signal of the moving object while cancelling out the noise of the static background. Every image where the object appears in slightly different positions contributes to the cumulative signal, and the background stars and galaxies, which do not move, get averaged away. When the team applied this method to the IRAs and Akari datasets, they found a candidate, a faint infrared source that appeared in both surveys, separated by 23 years of apparent motion, and that matched the predicted trajectory of Planet 9. The signal is extremely faint, sitting near the edge of what these older instruments could detect, but it is real enough to be taken seriously as a lead. One of the reasons this object evaded detection during the Wide-Field Infrared Survey Explorer mission, known as WISE, which surveyed the sky in 2010 and 2011, comes down to temperature. The predicted Planet 9 would exist in a range of temperatures, and if it falls at the colder end of that range, its thermal emission would peak at wavelengths that fall outside the primary detection bands of the WISE instrument. The planet could have been there the whole time, just slightly out of tune with the frequency that WISE was optimized to detect. The galactic plane adds another layer of difficulty. The center of our galaxy is an extraordinarily crowded region of space, dense with billions of stars, clouds of gas, and thick lanes of interstellar dust. All of these emit infrared radiation. If Planet 9 is currently projected against the star-dense background of the Milky Way's central bulge, it becomes almost impossible to isolate a single faint point source from millions of others. Astronomers searching for the planet in that region must sift through an enormous number of false positives. Every background galaxy, every faint star, every infrared-emitting dust particle becomes a potential mimic of the signal they are looking for. This is why the archival candidate from the 2025 study requires confirmation from a more powerful and modern instrument. The infrared signature identified in the IRAS and ACARI data is promising but not yet definitive. It needs to be captured by a telescope with a larger mirror, higher spatial resolution, and broader wavelength coverage to verify that it is truly a physical object rather than a processing artifact or an unresolved confusion of fainter sources. That confirmation effort is currently underway. Researchers are training the most powerful available telescopes on the specific coordinates flagged by the archival study. Meanwhile, a fundamentally different search strategy has been coming online, one that approaches the problem not through infrared archives, but through the most ambitious optical sky survey ever attempted. The Vera C. Rubin Observatory sits on the summit of Sarapachen in the Chilean Andes at an elevation of approximately 2,662 meters above sea level. It houses an 8.4-meter primary mirror and a camera, with a resolution of 3.2 gigapixels, meaning 3,200 megapixels. This is the largest digital camera ever built for astronomical purposes. Its imaging sensor measures approximately 1.65 meters in diameter, and its field of view is wide enough to capture 40 full moons in a single exposure. The observatory became fully operational in early 2026 and immediately began its primary scientific program, known as the Legacy Survey of Space and Time. This survey does not work like a traditional telescope that spends long hours staring at a single patch of sky. Instead, it functions like a cosmic video camera, sweeping across the entire available southern sky every few nights and recording everything it sees with extraordinary depth and precision. The technical specifications are remarkable. In a single 30-second exposure, the Vera Rubin telescope can detect objects down to an apparent magnitude of 24.5. This is already significantly deeper than any previous wide-field optical survey. But the real power of the system comes from accumulation. Over the course of the 10-year survey, each part of the sky will be imaged more than 800 times. When those hundreds of images are stacked and aligned, the effective sensitivity increases to a magnitude of 27.8. To understand what that means in practical terms, consider that the faintest stars visible to the naked eye on a dark night have a magnitude of around 6. Each increase of 5 magnitudes corresponds to a factor of 100 in brightness. A magnitude of 27.8 means the telescope can detect objects roughly 3 trillion times fainter than the faintest star your unaided eye can see on a dark, clear night. Planet 9, estimated at around magnitude 22 to 25, should fall well within the reach of the survey. The first peer-reviewed scientific paper produced using data from the Rubin Observatory's camera was published in January 2026. The paper reported the discovery of a large, fast-rotating asteroid designated 2025 MN45, located in the main asteroid belt between Mars and Jupiter. While this discovery is not directly related to Planet 9, it demonstrated something critically important. The observatory's software pipeline for detecting moving objects is working correctly. The detection of an asteroid requires the same basic technique needed to find a distant planet. You take images of the same patch of sky on multiple nights. You compare them and look for any point of light that has changed its position. Static objects, stars, galaxies, background sources remain fixed. Moving objects, asteroids, comets, and potentially undiscovered planets shift between images. The software flags these moving points automatically and submits them for human review. For a distant object like Planet 9 at several hundred astronomical units, the apparent motion would be almost imperceptibly slow. In a single night, it would move less than the width of a single pixel in most images. But over weeks and months, the accumulated drift becomes measurable. And over the course of a full year of the survey, even the slowest moving objects at the greatest distances should generate a detectable positional shift. The survey strategy involves revisiting each section of the sky hundreds of times, with the time gaps between visits optimized to catch objects moving at the speeds predicted for different kinds of solar system bodies. For Planet 9 specifically, researchers have calculated the expected speed across the sky based on the orbital parameters suggested by the gravitational evidence, and the observing cadence is designed to be sensitive to objects moving at exactly those rates. By the end of the first 1 to 2 years of its primary survey, if Planet 9 exists within the predicted range of masses and distances, and within the section of sky currently being prioritized, the Vera Rubin Observatory should have a strong probability of detecting it. The search area has already been substantially narrowed by the combination of theoretical modeling and archival infrared analysis. The telescope is not scanning the entire sky randomly. It is conducting a methodical sweep of the specific region, where the gravitational evidence most strongly predicts the planet should be. One of the most significant advantages of this new survey over all previous searches is the elimination of observational bias. Earlier attempts to find Planet 9 or to study the distant Kuiper Belt were limited by where specific telescopes were pointed and by the sensitivity of their instruments. This created a selection effect. Astronomers were far more likely to find objects in regions of sky that had been thoroughly surveyed, and less likely to find them in regions that had been poorly covered. The apparent clustering of known distant objects could therefore be, at least, partly explained by where astronomers were looking rather than by where the objects actually preferred to be. The Vera Rubin Observatory eliminates this problem almost entirely by imaging everything available from its location on Siro-Pachin with uniform sensitivity and cadence. It will produce the first genuinely unbiased census of the outer solar system. This census will either confirm the clustering of distant objects independent of any observational selection effect, or it will reveal that the clustering was an artifact of previous incomplete surveys. Either way, the result will be scientifically decisive. Even if Planet 9 is not found directly in the first few years of the survey, the discovery of tens of thousands of new Kuiper Belt objects will dramatically improve the statistical foundation for the hypothesis. Every new distant object added to the catalogue either strengthens the case for Planet 9 by clustering in the predicted direction or weakens it by appearing in random orientations. The data accumulates with each passing night, and the picture gets clearer. But the Vera Rubin Observatory is not the only tool in play. Astronomers are also looking at this problem from a completely different angle, using radio telescopes and interferometric techniques to search for the gravitational influence of Planet 9 on spacecraft that have already traveled to the outer solar system. The Pioneer 10, Pioneer 11, Voyager 1, and Voyager 2 spacecraft were all launched in the 1970s and have since traveled beyond the boundary of the heliosphere, the bubble of solar wind that surrounds the solar system. These probes are still being tracked by NASA's Deep Space Network, which measures their positions and velocities with extraordinary precision using radio signals. If Planet 9 exists and its gravitational influence extends as far as these spacecraft have traveled, there should be tiny but measurable deviations in their flight paths that are not explained by the known 8 planets and their moons. This approach has limits. The spacecraft are already very far from the predicted location of Planet 9, and the gravitational influence of such a distant object on their paths would be extremely subtle. But every additional constraint on the planet's location and mass is useful. ruling out certain orbital configurations using spacecraft. Tracking data helps narrow the search zone for optical and infrared surveys. As the search intensifies from multiple directions simultaneously, the scientific community has also had to grapple with a series of alternative explanations that do not require a new planet at all. These alternatives deserve serious consideration, because extraordinary claims require extraordinary evidence, and the existence of an undiscovered planet in our own solar system qualifies as exactly that. The most statistically motivated alternative was proposed independently by several groups who argued that the apparent clustering of distant trans-Neptunian objects might be entirely explained by where telescopes have been pointing. This was the observational bias argument, and it was taken seriously for several years. However, as we have discussed, the bias-corrected analyses by Beitigin Brown and others have substantially weakened this objection. The signal that remains after correcting for bias is still too strong to dismiss. The second alternative involves modified Newtonian dynamics, a theoretical framework sometimes abbreviated as MOND. This theory was originally developed in the 1980s by Israeli physicist Mordechai Milgram to explain why galaxies rotate faster at their edges than standard Newtonian physics predicts. According to MOND, the law of gravity changes behavior at very low acceleration. Rather than invoking dark matter to explain galactic rotation curves, MOND proposes that gravity itself operates differently below a certain threshold of acceleration. In 2023, researchers Catherine Brown and Harsh Mather applied an external field effect from MOND specifically to the solar system. Their calculations showed that the gravitational pull of the Milky Way galaxy as a whole could exert a subtle but measurable influence on objects in the outermost reaches of the solar system, where the Sun's gravitational dominance is waning. Under this interpretation, the clustering of Kuiper Belt objects is not caused by a nearby unseen planet, but by the galactic environment itself acting on objects that are nearly far enough from the Sun to feel the broader gravitational context of our galaxy. This is a genuinely interesting alternative. Not because MOND is universally accepted in astrophysics, it remains controversial, but because it raises the possibility that the outer solar system is gravitationally influenced by structures far larger than anything within it. The prediction it makes is distinct from the Planet 9 prediction, in specific ways that the Vera Rubin data should eventually be able to distinguish. A third alternative is perhaps the most exotic possibility on the table. In 2019, physicists James Onwin and Jakob Schultz proposed that the gravitational source responsible for the orbital clustering might not be a planet at all. It might be a primordial black hole. Primordial black holes are a hypothetical class of object proposed to have formed not from stellar collapse, but from density fluctuations in the very early universe, in the first fractions of a second after the Big Bang. If conditions were right, regions of extremely high density could have collapsed directly into black holes with masses ranging from a fraction of a gram to many times the mass of the Sun. A primordial black hole with a mass of 5 to 10 times the mass of Earth would be roughly the physical size of a grapefruit. If such an object was captured by the Sun's gravity billions of years ago or formed nearby during the solar system's early history, it would exert exactly the kind of gravitational influence we are attributing to Planet 9. It would have the right mass, it would follow a distant, elongated orbit, and it would be completely invisible to conventional optical and infrared telescopes, because it emits no light and has no surface to reflect or radiate heat. The signature of a primordial black hole would be different from that of a planet in one specific way. As a black hole moves across the sky relative to background stars, Its intense gravitational field would bend the light from those stars in a measurable pattern called gravitational microlensing. Stars passing behind the black hole, even at enormous distances, would briefly brighten and distort in a characteristic way. Detecting this microlensing signature would require monitoring millions of stars over long periods, looking for the brief, distinctive brightening events that would betray the presence of a compact gravitational source. The Vera Rubin Observatory, with its deep imaging and rapid cadence, is actually well suited to detect gravitational microlensing events. If Planet 9 is actually a primordial black hole, the survey might identify it through this entirely different channel, not by seeing a planetary disk, but by catching the black hole bending starlight as it moves. A fourth alternative involves not a single large object, but a distributed population of smaller ones. Theorists Antranig, Sifilian, and Jihad Tuma proposed in 2019 that the orbital clustering of distant trans-Neptunian objects might be explained by a massive, extended disk or ring of debris in the outer solar system, rather than a single concentrated mass. If enough small icy bodies were distributed throughout the outer solar system in the right configuration, their collective gravity could mimic the effect of a single large planet. The challenge with this explanation is observational. A disk with enough total mass to explain the clustering would contain enormous numbers of objects, all of which would be radiating infrared heat. The total thermal emission from all those small bodies should be detectable by the same infrared telescopes used to search for Planet 9. The fact that no such extended infrared emission has been detected yet is a significant constraint on this model. It does not rule it out entirely, but it makes the required configuration of the disk increasingly contrived. Additionally, detailed dynamical simulations of the disk scenario suggest that it would need to be extremely massive and precisely configured to reproduce all the observed orbital features simultaneously, adding more free parameters to a model while also requiring increasingly specific arrangements of those parameters is generally a warning sign in science. The more baroque a theoretical explanation becomes, the more suspicious one should be. What unites all of these alternatives is a shared problem. Each of them can explain some subset of the observations. None of them explains all of them as naturally and consistently as the Planet 9 hypothesis. This does not mean Planet 9 is correct. It means that the alternatives each carry their own unresolved tensions with the data. The scientific process demands that the Planet 9 hypothesis be if the Vera Rubin Observatory scans the entire predicted sky region over its survey lifetime and finds nothing, the Planet 9 hypothesis in its current form must be abandoned or fundamentally revised. That would not be a failure of science. It would be science working exactly as it should, systematically eliminating hypotheses through observation. But if the survey does find an object in the predicted region with the predicted mass and orbital characteristics, the implications extend far beyond simply updating the solar system map with a ninth entry. They reach into some of the most fundamental questions about how planetary systems form and why our solar system looks the way it does. When astronomers search for planets around other stars, they find that the most common type of planet in the galaxy is something called a super-Earths are planets with masses between roughly 1 and 10 times that of Earth, larger than our world but smaller than the ice giants Uranus and Neptune. They are extraordinarily abundant. Surveys suggest that nearly every star system in the galaxy contains at least one super-Earth, and many systems contain several. Against this galactic backdrop, our solar system looks strange. We have a rocky inner system topped at roughly 1 Earth mass with our own planet. We have a gas giant zone populated by Jupiter and Saturn, each dozens of times more massive than Earth, and we have an ice giant pair in Uranus and Neptune. What we appear to lack is the most common type of planet in the universe. This absence has puzzled astronomers since exoplanet surveys made the abundance of super-Earths clear. One popular explanation is that Jupiter's early formation may have disrupted the conditions necessary to build a super-Earth in the inner solar system. Jupiter formed very quickly, and its gravitational influence may have prevented the rocky material in the inner solar system from accreting into a larger world. But this explanation leaves open the question of whether a super-Earth might have formed elsewhere in the system and then been moved or lost. The NICE model of solar system formation, developed by a group of researchers working in Nice, France, in the 2000s, provides a framework for understanding this. The model describes a dramatic episode early in the solar system's history when the giant planets Jupiter, Saturn, Uranus, and Neptune were not in their current orbits. They formed closer together and then migrated to their present positions through a series of gravitational interactions with each other, and with the enormous disk of debris that surrounded the young sun. Some versions of the NICE model work better if the solar system originally contained 5 giant planets rather than 4. In these simulations, a 5th giant formed in the outer system and then underwent a close gravitational encounter with one of the other giants, most likely Jupiter or Saturn, that sent it flying outward into a very distant, elongated orbit. In many of these simulations, the 5th planet is eventually ejected from the solar system entirely, thrown into interstellar space by the cumulative effect of gravitational interactions. But some simulations show a different outcome. Some fraction of the cases result in the 5th planet being kicked not into interstellar space, but into a very distant, but still gravitationally bound orbit around the Sun. It escapes the chaotic inner zone of the giant planets, but it does not escape the solar system entirely. It settles into a cold, distant, highly elongated path far beyond the known planets. If Planet 9 is confirmed, it could be this missing 5th giant. It would be a world that participated in the violent early history of the solar system's giant planet formation, was gravitationally expelled to the distant outskirts, and has been orbiting quietly in the dark ever since. Its existence would transform our understanding not just of the current solar system, but of the process by which all planetary systems evolve. The implications extend further still. If Planet 9 is indeed a super-Earth stranded in the outer solar system, it becomes the nearest example of the most common type of planet in the galaxy. Today, super-Earths are studied through the light of their host stars, hundreds or thousands of light-years away. The measurements are indirect, filtered through the blinding glare of the star, limited by the sensitivity of our instruments across vast distances. Finding a super-Earth in our own solar system, at a distance of a few hundred to 1,000 astronomical units, would be transformative, even from Earth. With the instruments we have now, or will have within the next decade, we could study this world in extraordinary detail compared to any exoplanet. We could measure the thermal emission from its atmosphere and determine whether it has a thick hydrogen envelope or a thinner atmosphere made of heavier molecules. We could constrain its internal structure by measuring how its gravity perturbs the orbits of objects we have already catalogued. We could look for moons orbiting it, which would tell us about its formation history and the conditions in the outer solar system when the planets first formed over longer timescales. If Planet 9 is confirmed and its orbit is precisely determined, it becomes a natural target for robotic exploration, not immediately and not quickly. Even with the fastest spacecraft ever launched, a probe to an object at 500 or more astronomical units would take decades to arrive. Voyager 1, launched in 1977, has taken nearly half a century to reach. Just 160 astronomical units from the Sun, a mission to Planet 9 with current propulsion technology would take 50 years or more. but proposed. Technologies in active development might change that calculus. Laser propulsion systems capable of accelerating tiny probes to a significant fraction of the speed of light are being studied by projects like Breakthrough. Even at a fraction of the speed of light, a small probe could reach Planet 9 in a decade or less if such technology can be developed to maturity. More conventional but still ambitious mission concepts involve using powerful gravitational slingshots around Jupiter or Saturn, combined with advanced nuclear propulsion to achieve the velocities needed for a faster transit. The point is that confirmation of Planet 9 is not merely the end of one search. It is the beginning of many others. Every orbital parameter we determine from Earth-based observations becomes a constraint that narrows the window of opportunity for missions. Every measurement of its infrared spectrum from afar is a preview of what a visiting probe would find. The discovery, if it comes, initiates a cascade of scientific opportunities that could extend well into the latter half of this century. As of the middle of 2026, the status of the search can be summarized as follows. The gravitational evidence for a ninth planet has never been stronger. The 2024 analysis by Bettigen and Brown, showing that the survival of Neptune crossing objects requires an external, stabilizing mass at the 5 sigma confidence level, is the single most statistically robust piece of evidence yet produced. The archival infrared study from 2025 has identified a candidate object that appeared in data from 1983 and 2006 with a movement pattern consistent with the predicted orbit, and that candidate is currently being followed up with modern instruments. The Vera Rubin Observatory, now fully operational, is scanning the predicted region of sky with unprecedented depth and breadth. Its software is proven, its sensitivity is sufficient, and its observing strategy is optimized for detecting slowly moving objects at great distances. If the planet is where the evidence says it should be, the observatory is in a position to find it. The scientific community's mood has shifted noticeably over the past 2 years. The question is no longer primarily whether the gravitational evidence is real. The evidence is too consistent and too statistically significant to dismiss. The question is what the source of that gravitational influence is. A planet remains the most economical and consistent explanation. The next few years of data will either confirm that explanation or force scientists to consider increasingly exotic alternatives. It is worth pausing to appreciate what that either-or actually means. If Planet 9 is confirmed, we gain a 9th member of our solar system, the first major new planet discovered since Neptune in 1846, and we learn that our home system is less unusual than we thought. If it is not there, the gravitational clustering must be explained some other way, and the best alternatives involve either changes to the fundamental laws of physics at low accelerations or the presence of a primordial black hole orbiting the Sun. In other words, we cannot lose. Whatever the answer turns out to be, it is profound. Finding nothing where the gravitational evidence points would be, in many ways, more revolutionary than finding a planet, because it would force a fundamental revision of either our understanding of gravity or our understanding of the early universe. There is also a broader lesson here about the process of scientific discovery. The search for Planet 9 illustrates something important about how knowledge advances. It rarely comes from a single dramatic observation. More often, it comes from the patient accumulation of evidence from multiple independent sources, from the iterative refinement of theoretical models, from the development of new observational capabilities, and from the willingness to seriously consider and test alternatives. The infrared candidate from archival data, the statistical signal from orbital clustering, the survival analysis of Neptune crosses, the bias-corrected modeling, the commissioning of the Vera Rubin Observatory. The development of shift and stack techniques, the application of MOND to the outer solar system, the proposal of primordial black holes as an alternative, all of these represent different threads of a single, enormous scientific investigation. They converge, they overlap, they sometimes contradict each other, but together they are building a picture of the outer solar system that is richer, stranger, and more complex than anything the 8-planet model alone can describe. We are mapping the edge of our neighborhood, and the edge turns out to be much farther away and much more populated than we imagined even. 20 years ago, there remained significant open questions. The exact orbital location of Planet 9, if it exists, is still not pinned down to better than tens of degrees of sky. The mass estimate spans a range from roughly 5 to roughly 10 Earth masses, which is broad enough that it leaves open a wide variety of possibilities for the planet's composition and atmosphere. The question of whether it is truly a displaced giant planet that formed alongside the others, or a captured rogue planet that formed elsewhere and was caught by the sun's gravity at some later time, is not yet resolved by the current evidence. The internal structure of a world with 5 to 10 Earth masses is also not straightforward to predict. Such a planet could be primarily rocky with a thin gaseous envelope. It could be a mini Neptune with a significant hydrogen and helium atmosphere. It could be water-rich, with a deep global ocean of high-pressure water ice beneath a thick atmosphere. Each of these possibilities would represent a fundamentally different type of world, with different implications for what we would find if we ever sent a probe to visit. The pace of discovery is accelerating. The combination of the Vera Rubin survey, the James Webb Space Telescope's infrared sensitivity, proposed future space missions optimized for the outer solar system, and the continued refinement of archival infrared studies means that the evidence will compound rapidly over the next several years. Within 2 to 5 years, either a definitive detection will have occurred, or the Vera Rubin survey will have covered enough of the predicted sky region to significantly constrain or rule out the most likely orbital configurations. Scientists are not waiting passively for the telescope to deliver a verdict. New trans-Neptunian objects are being discovered and characterized on a regular basis. Each new distant object is a data point that either strengthens or weakens the clustering signal. The census of the outer solar system that will emerge from the first decade of Vera Rubin observations will be the most complete ever assembled, and it will allow tests of the Planet 9 hypothesis that are currently impossible with the small samples available from past surveys. The primordial black hole alternative is also being actively pursued. Researchers have proposed novel microlensing surveys, specifically designed to search for a compact gravitational object in the outer solar system. If such surveys detect the characteristic brightening signature of a black hole bending starlight, it would be one of the most extraordinary discoveries in the history of science, simultaneously confirming the presence of a new type of object in our solar system and providing the first direct detection of a primordial black hole, which would have profound implications for our understanding of the early universe and the nature of dark matter. The MOND alternative is likewise generating new predictions that can be tested, because MOND modifies the behavior of gravity in a specific mathematical way. It makes distinctive predictions about how the orbital distributions of outer solar system objects should look that differ in measurable ways from the predictions of the Planet 9 model. With a large enough statistical sample from the Vera Rubin survey, these different predictions can be compared against the data, and one framework can be favored over the other. Even the disk of debris alternative has testable consequences. If the clustering is maintained by a distributed disk of small bodies rather than a single planet, the total mass of that disk implies a detectable level of infrared emission that should be measurable with the right instruments. The absence of this emission in current data already constrains the properties of any such disk, and future space-based infrared telescopes will either detect it or definitively rule it out. What we are witnessing is science operating at its most sophisticated and most exciting level. A genuine mystery has been identified. Multiple hypotheses have been proposed and are being tested simultaneously by different methods. The evidence is being refined, the predictions are being sharpened, and the observational capabilities are improving year by year. The outcome is uncertain, but the framework for resolving it is firmly in place. The last time we discovered a major new planet, it was 1846. For 160 years after that, the boundaries of our solar system were considered essentially known. Pluto's reclassification as a dwarf planet in 2006 felt more like a subtraction than an addition. It was a contraction of what we considered our neighborhood. What is happening now is an expansion, not metaphorically, but literally. We are discovering that the outer solar system contains structure, architecture, and possibly entire worlds that our 8-planet model never accounted for. Whether the agent responsible for that structure is a 9th planet, a primordial black hole, a modified law of gravity, or something we have not yet imagined, the solar system is turning out to be larger, stranger, and more intricately organized than we thought. The edge of the map is moving outward, and somewhere in the cold, dark space beyond Neptune, trillions of kilometers from the nearest sunbeam, something is waiting to be found. If you find the search for Planet 9 as fascinating as the evidence suggests it deserves to be, then the best way to follow the story as it develops is to stay connected to the sources doing the work. The research teams publishing on this topic include some of the sharpest minds in planetary science, and the next few years of data from the Vera Rubin Observatory will be extraordinary to watch unfold. If you want to keep receiving clear, evidence-based breakdowns of science like this, subscribing and leaving a like helps. Make sure more content like this reaches the people looking for it. The next time an announcement comes about Planet 9, you will have the context to understand exactly what it means. And based on everything the current evidence suggests, that announcement may not be far off. To fully appreciate why the search for Planet 9 matters so much, it helps to understand the broader context of how we have mapped the solar system over time, and how many times we have been surprised by what we found at its edges. The story of planetary discovery is really a story of instruments catching up with physics. Every new tool humans built gave us the ability to see further and more precisely, and every time we looked further, we found something unexpected. The history follows a pattern: confident certainty about the extent of the solar system, followed by an unexpected discovery that pushed the boundary outward, followed by a new period of confident certainty, followed by another unexpected discovery. The ancient world knew 5 planets visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. These were the wondrous objects that moved against the fixed background of stars. For thousands of years, they defined the solar system. The idea that anything might exist beyond Saturn was not on the conceptual horizon. Then, in 1781, William Herschel was systematically mapping the sky with a telescope he had built himself when he noticed a disc-shaped object that moved relative to the background stars. He initially classified it as a comet. Within a few months of careful observation, its orbit proved it to be a planet. Uranus was the first planet discovered in the modern era, and its discovery instantly doubled the known size of the solar system. The edge of the map moved outward by a factor of roughly 2 overnight. The story of Neptune, which we have already discussed, followed 65 years later. But Neptune's discovery did not settle the question of whether more planets might exist even farther out. Almost immediately, astronomers began noticing small discrepancies in the orbits of Uranus and Neptune, and speculation began about a possible ninth planet. This speculation intensified in the early 20th century. Percival Lowell, the American astronomer and businessman who funded an observatory in Arizona, became convinced that gravitational disturbances in the orbits of the outer planets indicated the existence of a planet X. He spent years searching for it, and died in 1916 without finding anything. The search continued after his death, and in 1930, Clyde Tombaugh discovered Pluto, using a blink comparator device that highlighted moving objects against the star. Background: the discovery was announced on March 13, 1930, exactly 75 years to the day after Herschel first observed Uranus. But Pluto, it quickly became clear, was not what Lowell was looking for. Its mass was far too small to account for the gravitational disturbances he had identified. The discrepancies in the outer planet orbits that motivated the search turned out to be measurement errors rather than real anomalies. Pluto was a lucky accident, found not because it was causing the anomalies, but because the search, motivated by those anomalies, swept a large enough area of sky that Tombaugh happened to image Pluto along the way. For several decades after Pluto's discovery, the solar system was considered a 9-planet system, with Pluto forming a neat, if peculiar, 9th member. The edge of the known solar system was Pluto's orbit at roughly 39 astronomical units, plus the vague expectation of a cloud of comets at great distances known as the Oort cloud, which had been theoretically predicted but never directly observed. Then, in the 1990s, everything changed again. The development of sensitive charge-coupled device detectors, the same basic technology that eventually led to digital cameras, allowed astronomers to detect much fainter objects than was previously possible. In 1992, David Jewitt and Jane Liu discovered the first object beyond Neptune that was not Pluto. They called it 1992 QB1, and it orbited the Sun at about 44 astronomical units, slightly farther than Pluto. This discovery confirmed the existence of the Kuiper Belt, a region of the solar system beyond Neptune populated by icy bodies left over from the formation of the solar system. Gerard Kuiper had theoretically proposed such a belt in the 1950s, though his original reasoning was somewhat different from what was eventually confirmed. The confirmation of the Kuiper Belt again pushed outward our understanding of the solar system's extent. Throughout the 1990s and 2000s, the census of Kuiper Belt objects grew rapidly. Hundreds, then thousands of objects were catalogued. Pluto, once unique, turned out to be merely the largest known member of a vast population of similar bodies. This ultimately led to the controversial reclassification of Pluto as a dwarf planet in 2006, when the International Astronomical Union formalized criteria that Pluto did not meet. But the discovery of the Kuiper Belt was not the final boundary. As surveys deepened and covered more of the sky, objects were found at greater and greater distances. Objects with perihelia beyond the Kuiper Belt, beyond the gravitational dominance of Neptune, orbiting in the dark emptiness that had previously been assumed to be essentially empty. Sedna, discovered in 2003, was the landmark discovery in this population. Its orbit could not be explained by any known body in the solar system. Something had shaped it, something that no longer seemed to be there, or something we had never found. The theoretical framework that emerged over the following decade to explain Sedna and similar objects eventually evolved into the Planet 9 hypothesis. But along the way, several alternative theories about what had shaped these distant orbits were seriously considered. One early proposal was that a passing star might have perturbed these distant objects long ago. In the early solar system, the Sun formed within a stellar nursery, a dense cluster of hundreds or thousands of stars, all born from the same giant molecular cloud. In such an environment, close stellar encounters would have been relatively common. A star passing within a few hundred to a few thousand astronomical units of the Sun could have gravitationally disturbed objects in the outer solar system, pulling some of them into the highly elongated orbits we see today. This hypothesis has some appeal because it does not require a currently present object. The perturbing star would have long since moved away as the stellar nursery dispersed over millions of years. The orbits it created would be fossils of an ancient interaction, preserved in the outer solar system ever since. The problem with this explanation is that it predicts a somewhat different distribution of orbital orientations than what we actually observe. Stellar perturbations would tend to produce a roughly symmetric scattering of orbital inclinations and orientations, while the observed clustering of sednoids and extreme trans-Neptunian objects shows a much more structured alignment. The passing star hypothesis can explain why some distant objects have highly elongated orbits, but it struggles to explain why those orbits all point in roughly the same direction. Another early proposal involved an extended stellar encounter, not with a passing star, but with a binary companion to the Sun. Some astronomers have proposed that the Sun might originally have been part of a binary system, with a second star orbiting it at distances of hundreds to thousands of astronomical units. This binary companion could have gravitationally sculpted the outer solar system during the period when it was present, before eventually escaping the system or being disrupted by external gravitational perturbations from the galactic environment. This hypothesis, like the passing star proposal, has the appeal of requiring no currently present object, but it faces similar problems with the specific pattern of orbital clustering we observe. Binary star sculpting would tend to produce a more diffuse and symmetric signature than what the data shows. The Planet 9 hypothesis, by contrast, naturally explains the specific alignment of observed orbits through the ongoing gravitational influence of a single massive body whose location and orbital orientation can be precisely predicted from the observed clustering. It makes specific, testable predictions that can be either confirmed or falsified by direct observation, understanding. The history of these competing hypotheses helps clarify why the Planet 9 proposal has persisted and strengthened over the years while the alternatives have struggled. It is not that the alternatives are obviously wrong. In science, obviously wrong is rarely the situation. It is that the Planet 9 hypothesis is more specifically predictive, more consistent across multiple independent lines of evidence, and more directly testable than its competitors. The concept of testability is central here. A scientific hypothesis is only valuable if it can, in principle, be proven wrong. A hypothesis that is compatible with any possible observation is not a scientific hypothesis at all. One of the strengths of the Planet 9 model is that it makes clear, numerical predictions. The planet should be in a specific region of sky. It should have a mass in a specific range. It should be at a specific distance from the Sun. It should have a specific orbital period and eccentricity. These predictions can be checked. If observations are consistent with them, the hypothesis gains credibility. If they are not, the hypothesis must be revised or abandoned. The Vera Rubin Observatory Survey is specifically designed to perform this test. It will not merely search for Planet 9. It will either find it or rule out the most likely versions of the hypothesis. A null result from 10 years of Vera Rubin observations would be a scientifically decisive negative result, the kind that forces real theoretical progress. But let us think carefully about what a null result would actually mean. If the Vera Rubin survey covers the entire predicted sky region to the depth needed to detect Planet 9 at the predicted mass and distance, and finds nothing, that would mean one of several things. First, the planet might exist, but be at a greater distance than the current models predict, in which case it would simply be fainter and slower moving than expected. The survey might miss it at its predicted location, while it is actually located farther out along the same general orbital track. Second, the planet might exist but have a different mass than predicted, which would change its brightness and potentially put it below the survey's detection threshold. Third, the gravitational evidence might not require a planet at all, and one of the alternative explanations might turn out to be correct. Each of these outcomes would be scientifically interesting. The first would require extending the search to greater distances with even more sensitive instruments. The second would require revising the mass estimate from the gravitational evidence and searching for a fainter object. The third would force a fundamental reconsideration of either the orbital statistics or the underlying physics. What a null result would definitively rule out is the specific parameter space currently most favored by the evidence. Ruling out the most likely version of a hypothesis is progress, not failure. It narrows the possibilities and focuses future effort. This perspective, that negative results are as scientifically valuable as positive results, is important to maintain when following the Planet 9 story. The emotional stakes can make it feel like finding the planet is the only success and not finding it is failure. But science does not work that way. Whatever the Vera Rubin survey reveals, it will represent a major advance in our understanding of the outer solar system. The physical properties of the outer solar system are themselves worth examining in more detail, because they reveal something profound about how planetary systems are structured and how they evolve over billions of years beyond Neptune, at distances of 30 to 50 astronomical units from the Sun, lies the classical Kuiper Belt. This is a ring of icy bodies that formed in the outer solar system during the first few tens of millions of years of the solar system's history. Many of these objects are captured in resonance with Neptune, meaning their orbital periods are simple fractions of Neptune's orbital period. Pluto, for example, makes 2 orbits around the Sun for every 3 orbits Neptune completes. This 2-2-3 resonance is remarkably stable and explains how Pluto can remain in its current orbit despite its periodic approach to Neptune's path. Beyond the classical Kuiper Belt, at distances of 50 to a few hundred astronomical units, lies the scattered disk, a population of objects whose orbits have been perturbed by gravitational interactions with Neptune over billions of years. Scattered disk objects have highly eccentric, tilted orbits that carry them both close to Neptune and far into the outer solar system. They represent the remnants of a larger population of objects that originally formed in the outer solar system but have been dynamically disturbed since beyond the scattered disk, at distances of hundreds to thousands of astronomical units, lies the region where Planet 9 is predicted to reside and the region where sednoids have been found. This is the regime that current surveys are only beginning to explore in any systematic way. The objects found here are so distant and so faint that cataloging them requires the most powerful instruments and the most patient observational strategies. And beyond even this region, at distances of thousands to hundreds of thousands of astronomical units, lies the Oort cloud. This vast spherical shell of icy bodies is theorized to be the source of long-period comets. Comets that take hundreds or thousands of years to orbit the Sun and that arrive in the inner solar system from all directions. The Oort cloud has never been directly observed. Its existence is inferred entirely from the orbits of the comets it sends our way. The outer boundary of the Oort cloud may extend as far as 100,000 astronomical units from the Sun, which would be nearly 2 light-years. At that distance, the Sun's gravity barely holds these objects, and perturbations from passing stars or from the tidal influence of the galaxy, can dislodge them and send them inward. Planet 9, if it exists, would lie well inside the Oort cloud, but far beyond the Kuiper Belt and scattered disk. It would occupy a zone of the solar system that we currently know almost nothing about. A vast dark space between the familiar, mapped territory of the Kuiper Belt and the dimly inferred Oort cloud. The existence of objects in this intermediate zone, the sednoids and extreme trans-Neptunian objects, is itself remarkable. How did they get there? Their orbits are too distant to have been shaped by Neptune in the way that scattered disk objects were. Their perilia are too large to allow Neptune to interact with them significantly. Yet they must have arrived at their current locations through some physical process. This is the question that Planet 9 was invented to answer. A massive planet in a distant orbit could, over billions of years, gradually shift the orbits of objects that passed through its gravitational neighborhood, objects that originally formed in the Kuiper Belt, or that were scattered outward by Neptune, and that then happened to be perturbed by Planet 9, could find their perilia lifted to large values, while their orbits were simultaneously aligned with Planet 9's own orbital orientation. The process is called secular perturbation, and it operates extremely slowly, acting over timescales of hundreds of millions to billions of years. But the outer solar system has been here for 4.5 billion years, which is more than enough time for these slow perturbations to accumulate into the dramatic orbital architecture we observe today. This is actually one of the most elegant aspects of the Planet 9 hypothesis. It does not require a dramatic or sudden event. It does not require fine-tuning or coincidence. It requires only the long, slow, patient action of gravity across billions of years. The same mechanism that governs every other large-scale structure in the solar system. In this sense, the Planet 9 hypothesis is remarkably conservative. It invokes a ninth planet, but it relies on entirely familiar physics operating on entirely familiar timescales. The properties of the planet itself, if confirmed, would be intensely interesting from the perspective of planetary science. A world with 5 to 10 Earth masses sits in a mass range that we currently understand less well than either smaller rocky worlds or larger gas and ice giants. Rocky planets like Earth form through the accretion of solid material, building up gradually from dust and pebbles to planetesimals to protoplanets. Gas giants like Jupiter form differently, with a rocky core accumulating first and then triggering the rapid collapse of surrounding gas. When the core reaches a critical mass, typically around 10 Earth's masses, a planet of 5 to 10 Earth's masses sits right at this transition zone. It might be predominantly rocky, a giant version of Earth. It might be predominantly icy, a super version of Pluto, or it might have accumulated a significant gaseous envelope, putting it in the mini-Neptune category that is so abundant in other star systems. The answer likely depends on where and when in the solar system's history it formed. If it formed close enough to the Sun that temperatures were above the condensation point of water ice, it would be primarily rocky. If it formed beyond the snow line, where water and other volatiles condense into ice, it would incorporate large amounts of icy material. If it formed during the gas-rich phase of the early solar system, it might have accreted a significant atmosphere. These questions would be addressable with the right observations, even from Earth, though with difficulty. The temperature of the planet, measurable through its infrared emission, constrains the amount of internal heat it retains, which in turn constrains its composition and structure. The way it perturbs the orbits of known objects gives information about its mass distribution, and the dynamics of any moons it might possess would provide additional constraints on both its mass and its formation history. The temperature of Planet 9, if it exists, is one of the critical unknowns. At distances of 500 to 1,000 astronomical units from the Sun, the contribution of sunlight to the planet's surface temperature is negligible. The planet's temperature would be dominated almost entirely by its internal heat. A planet with significant retained heat from formation might be warm enough to maintain liquid water in a subsurface ocean beneath a frozen outer crust, though this would require specific conditions of atmospheric pressure and composition that are speculative at this stage. More realistically, Planet 9 would be an extraordinarily cold world, with surface temperatures of perhaps 40 to 80 Kelvin, which is minus 230 to minus 190 degrees Celsius. These temperatures are below the condensation point of most volatiles, meaning that any atmosphere the planet possessed would likely be frozen onto its surface. Nitrogen, methane, and carbon monoxide, the molecules that form the tenuous atmospheres of distant icy bodies like Pluto and Triton, might exist as thick ice layers rather than as gases. In such extreme cold, the planet might superficially resemble a scaled-up version of the icy dwarf planets we already know. But at 10 times the mass of Earth, even a predominantly icy world would have different interior conditions. The pressure at the center of a 10th mass body is high enough to produce exotic high-pressure phases of water ice, hydrogen, and other materials that do not exist naturally on Earth. The internal structure and geological history of such a world would be unlike anything in our current solar system. Catalog, all of this would be transformative. For planetary science, we have detailed knowledge of 4 rocky planets close to the Sun, 4 gas and ice giants in the middle solar system, and a swarm of small icy bodies in the outer system. We are missing the middle ground, the super-Earths and mini-Neptunes that are common throughout the galaxy. A 9th planet would fill in that gap in our solar system sample set in the most direct way possible, by providing a nearby object of the most common planetary type for in-depth study. The discovery would also have direct implications for the study of exoplanets. Currently, when we observe super-Earths around other stars, we do so through indirect methods. The transit method detects the tiny dip in a star's brightness as a planet passes in front of it. The radial velocity method detects the small wobble that a planet induces in its host star's motion. Both methods tell us about the planet's size, mass, and orbital parameters, but almost nothing about its composition, internal structure, or atmosphere. A planet 9 in our own solar system would be observable with instruments capable of direct imaging, spectroscopy, and eventually in situ exploration by robotic probes. Every observation of Planet 9 would provide a ground truth reference point for interpreting the indirect measurements of super-Earths around distant stars. The solar system would stop being an anomalous outlier and become, instead, the best studied example of the most common class of planetary system in the galaxy. The broader philosophical implication is worth dwelling on. For roughly 300 years after Copernicus proposed that Earth orbited the Sun rather than vice versa, the trajectory of astronomy has been one of successive revelations of mediocrity. Earth is not special. The Sun is not special. Our galaxy is not special. These are not diminishments, but expansions of perspective. Recognizing that the processes that shaped our corner of the universe are universal, and that the universe is far richer and more varied than any parochial view could suggest. The apparent absence of a super-Earth in our solar system had reversed this trend slightly. Here was one way in which our system seemed to be genuinely unusual, lacking the most common planetary type. The confirmation of Planet 9 would restore the trend, revealing that our system does have a super just tucked away in a distant dark corner, where we had not yet looked carefully enough. This is a satisfying narrative from a scientific perspective, not because it confirms a preference, but because it would mean that the processes of planet formation are even more universal and consistent than we previously thought. Wherever you look in the galaxy, super-Earths form. They might end up close to their stars, as in most of the exoplanet systems we observe, or they might end up far away in the cold outer reaches of their systems, as Planet 9 apparently did. But they form the detection technology that will find Planet 9, if it is there, has been assembled over decades of incremental improvement. The Shiftan stack technique, the infrared archive mining, the bias correction methodology, the unbody simulation capabilities that allowed Betagen and Brown to model the orbital dynamics of the outer solar system, the commissioning of the Vera Rubin Observatory with its gigapixel camera and automated source detection pipeline. All of these represent the accumulated work of thousands of scientists across many decades. This is how big discoveries actually happen, not in a single flash of insight, but through the patient, iterative, collaborative accumulation of knowledge and capability. The moment of discovery, when it comes, will belong to the entire enterprise of planetary science, not to any single instrument or individual. We are now closer to that moment than we have ever been. The gravitational case is the strongest it has been. The observational infrastructure is the most capable it has ever been. The search area is the most constrained it has ever been. And the candidate from the archival infrared study has given researchers a specific target to confirm or rule out. The next announcement about Planet 9 might come from the Vera Rubin Observatory detecting a slow-moving object in the southern sky. It might come from astronomers confirming that the infrared candidate from the IRAs and Ikari data corresponds to a real physical object with a Rubin optical detection. It might come from an unexpected source entirely, a novel survey strategy or a reanalysis of existing data that reveals something that previous searches missed. Whatever form it takes, the announcement will change our maps in the most literal sense. The solar system we grew up learning about, the one with 8 planets arranged in orderly rings around the sun, with the icy Kuiper Belt at the edge and nothing beyond, will be replaced by something larger and stranger and more architecturally complex. The outer solar system is not an empty wilderness. It is a structured environment, organized over billions of years by the gravitational interplay of masses we have not yet fully catalogued. Every object we find out there, every distant world on an elongated orbit, every ice-covered body drifting in the dark, is a clue to the history of our solar system and to the processes that govern planetary systems throughout the universe. The hunt for Planet 9 is, at its deepest level, a hunt for understanding. Understanding how our solar system formed, understanding what kinds of planets exist and where they can be found, understanding whether the laws of gravity, as we know them, accurately describe the behavior of matter at the very edges of our gravitational neighborhood, understanding whether our neighborhood is typical or exceptional among the star systems of the Milky Way. These are not narrow technical questions. They are among the most fundamental questions in planetary science, and they are on the verge of being answered. The outer edge of the solar system is calling, and for the first time in the history of astronomy, we have the tools, the data, and the theoretical framework to hear the answer, to truly grasp the scale of what we are dealing with when we talk about Planet 9. It helps to build the spatial context from the ground up, starting with something we can intuitively grasp and expanding outward until the numbers become almost philosophical. Imagine traveling from Earth to the Sun. That distance is approximately 150 million kilometers, and we call it 1 astronomical unit. Light covers this distance in about 8 minutes. A passenger jet flying at roughly 900 kilometers per hour would take approximately 19 years to complete that journey. The distance is vast by any human standard. and yet it is the baseline unit we use to measure everything else in the solar system. At 1 astronomical unit, we are at Earth. At 5.2 astronomical units, we reach Jupiter, the largest planet. At 9.5 astronomical units lies Saturn with its magnificent rings. Uranus sits at roughly 19 astronomical units. Neptune, the outermost known planet, orbits at about 30 astronomical units from the Sun. Pluto, once the 9th planet and now reclassified as a dwarf planet, has an average orbital distance of about 39 astronomical units, though it follows an eccentric path that takes it as close as 29 and as far as 49 astronomical units. At 44 astronomical units, roughly where the outer edge of the classical Kuiper Belt is traditionally placed, we are already at a distance where light takes over 6 hours to make the journey from the Sun. A communication signal sent from a spacecraft in that region to Earth takes 6 hours one way. A round-trip conversation with a probe at the outer Kuiper Belt would involve a 12-hour delay. Now consider that Planet 9 is predicted to orbit at a distance ranging from roughly 200 astronomical units at its closest approach to the Sun, all the way out to potentially 1,000 astronomical units at its most distant. The midpoint of its orbit might be somewhere around 500 to 600 astronomical units. At 600 astronomical units, light takes over 83 hours to travel from the Sun to the planet. A radio signal from a probe exploring that world would take 3.5 days to reach Earth, and 3.5 days to receive a reply. In terms of physical scale, an object at 600 astronomical units is roughly 90 billion kilometers from the Sun. If you drove continuously at highway speed, it would take you well over 10,000 years to cover that distance. It is a number that resists intuitive comprehension, and yet, in the context of our galaxy, it is absurdly close. The nearest star system to our Sun, the Alpha Centauri system, is at a distance of approximately 268,000 astronomical units. Planet 9, at 600 astronomical units, is less than 1/4% of the way to the nearest star. It is our immediate astronomical neighborhood. This scale perspective is important for understanding the nature of what a detection would mean. We are not talking about reaching out across the galaxy to find this world. We are talking about searching our own backyard, an extended backyard to be sure, but our own system nonetheless. The light travel time from a probe at Planet 9 would be days, not years or decades. The communications delay, though significant, would be manageable. The distance, though staggering in human terms, is a tiny fraction of interstellar distances. A mission to Planet 9 would represent the ultimate extension of our solar system exploration program, but it would not be a departure from it in the way that interstellar travel would be. We send probes to the gas giants, which are decades of travel away at current spacecraft velocities. We sent the New Horizons spacecraft to Pluto, arriving 9.5 years after launch. A direct mission to Planet 9 would require new propulsion technology or extraordinary patience, but it is within the conceptual horizon of what future generations of planetary scientists might realistically accomplish. The physics of reaching such a distant target with current technology deserve detailed exploration, because they illustrate both the challenge and the opportunity. The fastest spacecraft ever launched by humanity is the Parker Solar Probe, which achieved velocities near its closest approach to the Son of Condor, around 700,000 kilometers per hour, by exploiting multiple gravitational assists from Venus. But Parker Solar Probe is not heading toward the outer solar system. Its trajectory is deeply inward bound. The spacecraft that have traveled furthest from Earth are the Voyager probes. Voyager 1, launched in September 1977, is currently moving at roughly 61,000 kilometers per hour relative to the Sun and has reached a distance of over 160 astronomical units. At that rate, reaching 500 astronomical units would require an additional 40 to 50 years of travel beyond its current position. A spacecraft launched today on a similar direct trajectory would take roughly 70 to 80 years to reach the inner portion of Planet 9's predicted orbit. This is obviously impractical for a crewed mission and is challenging even for a robotic one, given the decades-long development and operational timescales involved. But advanced propulsion concepts could change this. Nuclear thermal propulsion, which uses a nuclear reactor to heat propellant to higher temperatures than chemical rockets can achieve, could roughly double the velocity of a spacecraft compared to conventional propulsion. Nuclear electric propulsion, which uses nuclear power to drive ion engines over long periods, could achieve sustained accelerations that would allow much higher final velocities for missions to the outer solar system. The most dramatic possibility involves laser propulsion concepts like those explored in the Breakthrough Starshot initiative. This program investigated the feasibility of using powerful ground-based laser arrays to accelerate gram-scale probes to a significant fraction of the speed of light for potential interstellar missions. A far less ambitious version of this concept, using laser sails to accelerate larger probes to perhaps 1% of the speed of light, could potentially reach Planet 9 in a matter of years rather than decades. But all of these concepts remain speculative or immature. The practical reality is that if Planet 9 is discovered in the near future, the first decades of its scientific study will be conducted entirely from Earth and from spacecraft in the inner solar system. Telescopes on the ground and in orbit will measure its brightness, its spectrum, its position, and its motion. Radar arrays might bounce signals off it and detect the return echo, directly measuring its distance to extraordinary precision. Astrometric observations over many years will refine its orbital parameters to the point where its future position can be predicted with high accuracy for centuries into the future. All of this accumulated knowledge would form the scientific foundation for planning any eventual mission. The more we know about the planet before a probe departs, the more specifically the probe's instruments can be designed to answer the most important remaining questions. This is exactly how the exploration of the known outer solar system unfolded. Pioneer and Voyager made the first flybys and returned basic data. Cassini spent 13 years in orbit around Saturn and returned science that completely transformed our understanding of that system. New Horizons gave us our first detailed look at Pluto. Each mission was informed by all the science that came before it. The discovery of Planet 9, whenever it comes, would initiate this same progression for a new target. The initial detection, followed by characterization from Earth, followed eventually by the launch of one or more dedicated missions, followed by the possibility of orbital insertion and extended exploration if technology advances sufficiently. This is the long arc of solar system exploration, and Planet 9 would be its next chapter. There is a philosophical dimension to all of this that deserves acknowledgement. The search for Planet 9 is, on one level, a highly specialized technical problem in observational astronomy. But on another level, it is a reflection of something fundamental about the human impulse to understand our place in the universe. Every civilization in history has looked up at the night sky and tried to make sense of it. The planets were recognized as special in antiquity precisely because they moved against the fixed background of stars, showing that the universe was not static. The ancient astronomers who tracked those wandering lights across the sky were doing the same thing that Batygin and Brown do today. noticing that something in the sky is behaving in an unexpected way, and trying to figure out why. The specific tools and techniques have changed beyond recognition. Ancient astronomers used their eyes and simple geometric models. Modern astronomers use gigapixel cameras, supercomputer simulations, infrared space telescopes, and statistical frameworks that would have been incomprehensible even a century ago. But the underlying drive is the same: the determination to understand the architecture of the world we inhabit, to map out our neighborhood and know what is in it. The outer solar system is the last major unmapped territory in our immediate cosmic vicinity. We have good census data for the inner solar system. We have explored the gas giants and their moon systems with dedicated missions. We have surveyed much of the Kuiper Belt, but the region from a few hundred to 1,000 astronomical units remains largely uncharted. Planet 9, if it is there, would be the flagship discovery in the exploration of this territory. But it would almost certainly not be the last. The Vera Rubin Observatory's 10-year survey of the southern sky will produce a catalogue of solar system objects that is orders of magnitude more complete than anything that has come before. Hundreds of thousands of Kuiper Belt objects will be catalogued where we currently have only a few thousand. Thousands of objects in the scattered disk and extended scattered disk, the populations from which the most extreme trans-Neptunian objects are drawn, will be found and characterized. The census will be comprehensive enough to test not just the Planet 9 hypothesis, but a whole range of theories about the formation and evolution of the outer solar system. This is the broader scientific legacy of the search for Planet 9. Whatever its specific outcome, we will understand the outer solar system dramatically better than we do today. We will be able to test dynamical models against a statistical sample that is rich enough to distinguish between competing theories. We will discover objects that challenge our current understanding in ways we cannot anticipate, and we will be better equipped to interpret what we find around other stars, because we will have a detailed map of our own system to compare against. The outer solar system is not just a backyard curiosity, it is a time capsule. The objects preserved in it, particularly those in the most distant and dynamically inactive orbits, have changed little since the solar system formed 4.5 billion years ago. They carry within them the chemical and structural record of the conditions that prevailed in the young solar system. The composition of the disk of gas and dust from which all the planets formed. The distribution of organic molecules and water, ice that was present in the early system and that likely seeded the inner planets with the raw materials for life. The study of trans-Neptunian objects is thus connected, through a chain of scientific reasoning, to the question of how life appeared on Earth. The water in our oceans, the carbon in our cells, the nitrogen in our atmosphere, these were not always here. They were delivered from the outer solar system, carried inward by comets and asteroids during the first billion years of the solar system's history. The compositional inventory of the outer solar system tells us what was available for this delivery, and what conditions the early Earth received. Planet 9, as the largest and most massive object in this outer zone, may have played a specific role in shaping that delivery. If it shepherds the orbits of distant objects, keeping them in stable configurations over billions of years, it may also regulate the supply of comets and icy bodies that reach the inner solar system. A system with a Planet 9-like object in the outer reaches might have a different rate of cometary bombardment of its inner planets than a system without one. This is speculative, but it connects the existence of an outer planet to questions about the habitability of the inner planets of a system. The astrobiological implications are modest but real. If super-Earths in the outer solar system are common, as the Planet 9 hypothesis would suggest, then every planetary system with a similar architecture to our own might include a distant icy world shepherding the orbits of its outermost debris belt. The rate of cometary delivery to the inner planets in such systems might be systematically different from systems where no such outer planet exists. Over geological timescales, differences in cometary bombardment rates affect the water inventory of inner planets, the delivery of organic molecules, and the frequency of mass extinction events caused by large impacts. This is speculative, because we are extrapolating from a single data point, which is our own solar system. But it illustrates the way in which planetary science, at its deepest level, is connected to the question of life in the universe. The structure of a planetary system is not just an aesthetic or taxonomic matter. It is an environment, and the nature of that environment shapes the conditions under which life can arise or persist. The conformation of Planet 9, in this light, is not merely an astronomical milestone. It is a contribution to the ongoing effort to understand what kinds of planetary environments exist in the galaxy and which of them might support the emergence of complex chemistry and biology. Every piece of knowledge about the structure of the solar system is a data point in this larger inquiry as we wait for the data to accumulate. As the Vera Rubin Observatory sweeps its camera across the southern sky night after night, as the archival infrared candidate is followed up and either confirmed or rejected, as new trans-Neptunian objects are catalogued and their orbital parameters added to the growing statistical database, the science is progressing exactly as it should, patiently, systematically, with rigor and intellectual honesty about what the evidence does and does not yet establish. The search for Planet 9 exemplifies the best of what science is. It is empirical, driven by data rather than by wishful thinking. It is falsifiable, making specific predictions that can be tested and that will be tested. It is collaborative, drawing on the work of hundreds of researchers across multiple countries and disciplines. It is cumulative, building on each previous observation and analysis to sharpen the picture. And it is humble, taking seriously the possibility that the current best explanation might be wrong, and that the truth might be stranger and more interesting than our current models suggest, whether Planet 9 is found in the next few years or not. The outer solar system will have revealed itself to be a far richer and more complex environment than we imagined when the 8 planets of our textbooks were considered the final word on what our solar system contains. The maps are being redrawn, the boundary of the known is being pushed outward, and whatever is waiting in the cold and dark beyond Neptune, it is already changing how we understand the place we call home, the universe. It turns out rarely runs out of surprises, and the most surprising thing about the outer solar system may be that we are only now beginning to really look.